Hello, everyone. I'm very happy to see that SMLQC is going strong, now with the third edition in the US. I want to thank Kostas for making this edition possible and doing a wonderful job in organizing it. Every 2 years in this symposia, we witness how AI is making quantum leaps in reshaping quantum chemical research. In my talk, I will provide a snapshot of the progress in this field from our research group. What we now ultimately want with AI is that we communicate with it in natural language and tell it what we want to do. So, for example, if you want to calculate, simulate infrared spectrum of a molecule, you just want to tell, okay, please simulate the spectrum. And AI is now capable of doing this and provide you spectrum with explanations. So this is not science fiction anymore. Here is the video of how we do it on our online platform, which you can also play with. So here we ask to generate XYZ structure of a hexagonal molecule, and it's all integrated with a nice GUI. So you can open the structure once it's generated without human input. And so you don't need to prepare XYZ coordinates anymore for simple molecules. And so now you ask it to calculate infrared spectrum of this molecule. So after some thinking, it asks the user to confirm the calculation parameters, and then you finally see the spectrum generated for the user. So here you saw that it's not was just all done in natural language and easily understandable for even beginners in quantum chemistry. So anyone can talk with it. But you also see that the spectra which are generated are matching experimental ones quite well. Also, the calculations were done quite fast. And this is all possible by a very unique combination of using AI to talk with the user, but also using AI methods to perform the simulations fast and accurately. That was a very simple example. It was just two tasks to generate structure, calculate infrared spectrum. But in principle, in quantum chemistry and computational chemistry, we want to perform more complex simulations. And one typical is to calculate thermochemistry for chemical reactions. And if we ask now AI agents to, and this AI assistant to do this, it will come up with a plan, extract structures and perform calculations and analyze results, and it will give you the final summary with reaction energies and thermochemical analysis. Again, here is a video demonstrating how we do this online. So we ask to calculate reaction energies, thermochemistry for this other reaction between very simple molecules and ethene and 1,3-butadiene. So we don't even tell what is the product. So it's capable to understand what would the product be. And so it fetches initial XYZ structures for these molecules. And after it's, so again, without human providing XYZ structure. And as you can see, these structures are very reasonable. So the user can check them online. And while it's thinking, so it will perform the calculations now using AIChem2 method, which I will talk about later. And the summary of the results is generating in a while, providing the energies and Gibbs free energies for this reaction. The accuracy is pretty decent compared to higher level methods. And the whole workflow, these calculations were done in 5 minutes. So if you ask any undergraduate students, graduate students to do this or try yourself, you will definitely spend more than 5 minutes to do this by setting up all the calculations, finding where the energy is located, and or writing some scripts to do that and calculating. So this is really accelerating quantum chemical simulations. Now, this is all done by integrating many components, AI agents, of course, but also the key is also providing this Atomistic Hub, which is an online platform to do these simulations packed with GUIs. And we have quantum chemical machine learning methods there via emulator. And it can provide some reports and analysis for you. For more complex workflows, it has an orchestration agent which designs, which coordinates all these single task agents such as geometry optimization, frequency calculations, and then it provides a result analysis to the users. So in a nutshell, what it can do is perform many different simulations with quantum chemical methods, ab initio, DFT, some empirical ones, different machine learning methods, universal models, which are now very popular. Also extended now to like user-trained models, and combination of methods, some of which I will talk about, like these AIKM methods. And it can perform simulations ranging from geometry optimizations to spectroscopy, which you saw like for infrared spectra, but also UV spectra, thermochemical simulations you saw also, and like transition state search. So we also extended it now to other tasks like Raman spectra and so on, and model training too. In the background in this platform, the core software ecosystem is Emulatum, which we developed from 2013. And it really enables all these tools for AI agents because it has a very wide repertoire of different methods and simulations. So it's very organically combined workflows. None of these methods are overcoming the limitations of physics, so they are all based on Schrödinger equations. So here there is no miracle. And we this year celebrate 100 years of Schrödinger equations. That's why it's very appropriate to think the impact of it right now in the age of AI. Because at the end, from 1925, the equation is the same, but even back then it was realized that to solve it, we need approximations. And in my view, AI and machine learning is an ultimate approximation to the Schrödinger equation. It learns from data generated at it. And before machine learning, we really had to struggle between like cost and accuracy trade-off, where one of the best methods striking this balance are DFT approaches, making them so popular. And the biggest problem was that if you want something faster, then usually it's less accurate. And if you want something more accurate, it's very often unaffordable to your applications. So that was the motivation why all these machine learning potentials now. So for topic, because they really break through these limitations, so they can achieve low cost and high accuracy. But at the end, they are still based on the same Schrödinger equations. They just learn implicitly through the data its underlying principles. So one of the first practical methods which was combining machine learning and quantum chemistry to do practical realization, which doesn't need much of fine-tuning, although it can be done. It is AIKM1 method, which is pretty robust too. So in contrast to many pure machine learning potentials, it's physics. It has physics-based baseline. That's why it will not have too many crashes like we see in machine learning potentials. And the speed is very decent. So it is semi-empirical speed. That's why you can do quite big molecule optimizations. I will show you also bigger ones later. But for this one is 2 CPU minutes. With DFT, it would be much slower, 1,200 CPU minutes, and the accuracy of DFT calculations wouldn't be even better compared to the X-ray optimized geometry. So this robustness is based on combining some empirical methods baseline and then doing delta learning corrections for energies and forces plus default corrections to ensure correct treatment of non-covalent interactions. And the nice thing about it is that we elevate some empirical accuracy to almost couple cluster accuracy. How we do this? So this is based on delta learning, where we train first delta learning model on DFT data, which is more abundant. Back then, it was quite big data, almost 5 million. Nowadays, of course, it's not so big with new data sets. And we then transfer learn this correction to on only 500,000 data points to couple cluster accuracy. So if you compare to different benchmark sets with DFT, for example, then AIK1 is really doing very well for many properties. So if you see it's green, so the errors are quite small and not for everything, but especially well is doing for ground state properties of neutral closed shell compounds, although it's not limited to them. And for these compounds, it's really approaches couple cluster accuracy for many applications, which allows you to do very accurate thermochemistry and calculate, for example, isoformations, and you can optimize structures, as I showed you before. Another way to use it is to apply it to calculate some observables like infrared spectra. And one way to calculate infraspectra is to propagate quite expensive path integral MD. For small molecules, it's doable within reasonable amount of time, like here 1.5 CPU hours, and then you get a pretty good agreement with experiment in terms of positions and intensities to some extent. So this is because of underlying high quality potential. And there are some limitations for this method. That's why we constantly improve them. For example, if we look at the performance for out of the distribution, like transition states, which were not in the training data set, so we benchmarked on different types of chemical reactions, and then unfortunately, IKM1 was not better than DFT approaches like Bisrelief. It was a bit better than baseline semi-empirical methods, not showed here. It is better than pure machine learning potentials like ANI1CCX, but it was definitely not better than even DFT approaches. And that's a big limitation for computational chemists. That's why in the next generation AIKM2, we improved it to reach close to DFT accuracy. But for many applications, it is doing quite good, even better than DFT. So that was recently published as a cover also in Chemical Science Journal. And here is an example what it can do if you want to propagate massive simulations. Is the tool to go. So with this method, AIKM2, you can propagate 1,000 quasi-classical downhill MD trajectories overnight. If you want to do it with DFT, it will take you 160 CPU years. And that was indeed done in 2017 by experts in the field, where they use Bisrelief methods. And back then, they used a high-performance computing cluster to do the simulations, and they maxed out with something like maybe a bit more than 100 MD trajectories. So we get higher precision by doing more trajectories, but also for this particular reaction, what we have is better agreement to couple cluster energies, for example, for transition states and for minima than this DFT approach. So we not just get faster, higher sampling in terms of more trajectories which we propagate, but we also get higher accuracy for these minima and transition states, which overall should result in a higher quality MD trajectory. And that's why we revise the product distribution from this ambimodal reactions, where we see post-transition state bifurcation to from 9 to 91% with DFT to 3 to 97. And in addition to that, what we have is uncertainty estimates of our calculations where you see these error bars plus minus like 1.8, 2.5, which might be not great because it's still less than chemical accuracy, but at least you get some idea how well it is. And that's something that is totally missing from DFT, because in DFT you have no idea whether it's good or bad unless you or until you compare it to his better quality quantum chemical results or experiment. That's why I would argue that modern methods like AIQM2 not just fast and accurate, but also trustworthy, because you can look up the errors. And they are not, so this method is not limited to reactions, so it can be applied also for infrared spectra. And in fact, this method was used in these infrared spectra simulations I showed you in the very first slides. The agreement to experiment is similar to DFT, but the speed is much faster. It can treat also quite big molecules and systems. So here, with these aggregates, one CPU a day, so parallel computers, it's much faster than a day. For 1,000 atoms, you can optimize it and get quite decent agreement with crystallographic structure. For some molecules, agreement is less, but the systems are also quite big, and then you can treat them very fast, which enables you to use it out of the box without any fine-tuning to explore your systems. And now independent research groups adapted our methods to do applications in protein drug systems, and with our collaborators, we also see that these methods really have very good results for protein ligand interactions. I was talking about ground state mostly, while we are also we have big interest in simulating excited state properties, including fluorescence, and AIK1 can also do it because it's based on semi-empirical methods, which provides you access to everything which semi-empirical methods has, like wave function, and can calculate also excitation energies and oscillator strengths, transition dipole moments. So here, for this molecule, it is fluorescence, but when we put C60 fullerene inside, then AIK1 predicts quenched fluorescence. So you can optimize this S1 minimum of this system and see that it's fluorescence quenched, and that's indeed what was observed in experiment. So this tool provides very nice screening way for different molecules to see whether they are fluorescence, which might be also useful for investigating aggregation-induced emission or photocatalysis. And because it is, again, like provides all the necessary quantities required for example, reactive NIMD trajectories propagation. It can be used in surface hopping dynamics. We can calculate quantum yields, and for this particular molecule, azobenzene, quantum yield is quite similar to the experimental one. Although this method still remains an empirical one, so making limitations in terms of speed. So if you want to go even faster, then we need to go to pure machine learning potentials. And in pure machine learning potentials, there was not much choice in terms of universal ones, right? So what I was showing you before, all these methods can be used out of the box. Here, for excited states, we didn't have a universal model which could be used out of the box. That's why our attempt to do this is the first ever excited state machine learning potentials, Omni P2X, which is designed with this goal to provide some universal transferable way to calculate various molecules at the machine learning potential speed. So currently it states its accuracy is a bit worse than TD-DFT, which it was trained on, but it is better than semi-empirical methods, as we'll see later. And via some small fine-tunings, so with small data, you can get accuracy to higher levels and higher robustness. So the application of this approach, the most straightforward one is to calculate UV spectra. And if you look at single point convolution spectra, so done for single equilibrium geometry, they're quite decent compared to TD-DFT reference, although not perfect. But taking into account that this is pure machine learning potential speed, it is way, way faster than even semi-empirical methods, and you can use it for screening. And the agreement for many thousands of molecules for which we tested this spectra similarity of OmniP2X is closer to TD-DFT than of semi-empirical TD-DFTB or ODM2 or CES approaches. And if you throw in a bit of training points at your target level, you can fine-tune it to do well enough even UV spectral simulations via nuclear ensemble approach, where you don't need to play with broadening factors, and then you will recover a bit of vibrational effects. Now, another big advantage of having universal models is that you can simulate with higher robustness non-abiotic dynamics after fine-tuning. So if you take it out of the box, it's still not working correctly from non-abiotic dynamics, while the biggest advantage is that it will require much fewer points if you want to upgrade it to your target level for your target molecule. And if you don't do any transfer learning, what usually happens during some active learning, adaptive sampling procedures is that you will, before your convergence, you will see many of the physical structures like these broken ones or very highly deformed ones, because models trained from scratch, they don't know underlying physics, so they have to learn all of this from the data. If you do transfer learning, it already knows lots of physics, so it's basically just fine-tunes itself to make predictions for your particular situation better. And if you look at this plot, so this is a fraction of training data which you need to get reasonable results. And if you do fine-tuning, so this transfer learning, you see that basically almost all trajectories are stable, even with very, very few data if you fine-tune universal OmniP2X. And if you don't do any fine-tuning, so if you do it from scratch, you need increasingly more points to get stable trajectories. Now, I've told you that about all these approaches, and I started with AI agents, and I will finish with AI agents because that's what will happen in the future. All these tools which we are developing are very easily integrated into autonomous research. And if previously it might have been difficult to apply these methods by learning how to do these new methods, how to use them for simulations, how to adapt them. Now it's becoming easier and easier with fully autonomous computational chemistry with AI. And if you want to learn more, so we have a book with 65 authors, but also an online course which I'd like to update from time to time with newest information. And before I finish, I'd like to thank to my students both in Xiamen and in Poland. So in Xiamen, I have a bigger group. In Poland, I have 2 PhD students who are doing a really great job in all these directions I showed you, from ground state to excited states, machine learning models to autonomous research with AI agents. And so now I have more people in 2025 joining in Xiamen. And I'd like to thank you for your attention. And if you want to follow more for our updates, you can subscribe to our channels too. Thank you very much.